If you are deciding what to read first, this version treats the list as a guided map rather than a ranking wall. Each paper opens on its own compact source figure. Then, the animation rebuilds the mechanism underneath it. The route is for readers choosing papers, builders looking for usable recipes, and researchers looking for transferable questions. The SAM 3D figure starts on masked object examples, then drops to the model split, where one crop becomes geometry, texture, and layout. The route climbs through staged human and model data collection, follows the multi-stage training loop, and lands on evaluation and scaling evidence showing why the data engine matters. The intuitive move is simple. A mask is not the output. It is the handle that lets the system ask for an editable 3D object. Synthetic renders, model-in-the-loop proposals, and artist preference feedback keep expanding the cases the model can survive, so clutter and occlusion become data problems rather than one-off failures. B. 3. Seg starts at the left problem panel. Only a 3D Gaussian splat scene and a text prompt are assumed, not preset cameras, masks, or retraining. Candidate views become possible questions. Analytic expected information gain chooses the most useful view, and the selected SAM2 mask updates Beta Bernoulli beliefs for every Gaussian. The mechanism is active perception in miniature. Instead of asking the segmenter to solve the whole 3D scene at once, the system asks the best next camera question, converts a 2D mask into evidence, and sharpens the splat probabilities. That is why the result can stay training-free while still moving toward a clean target mask. D. 4RT begins with the task table. Point tracking, point clouds, depth, and camera estimates are all query variants, not separate pipelines. The figure follows a video point into the query tuple, through one global memory decoder, down to reconstruction examples, and finally to the efficiency plot showing why this interface matters. The key idea is to make 4D reconstruction feel like asking a memory a precise question. A query names a source point, target time, and camera context. The same dynamic representation can answer with a track, depth, point cloud, or camera information, so the paper replaces many dense heads with one reusable query interface. .4D RGPT starts on the marked R1 box across frames because the question is not captioning a whole video, but keeping one region grounded through 2D, 3D, and time. The callouts contrast the baseline's uncertainty with explicit depth and temporal cues, drop into P4D distillation from an expert 4D model, and end on benchmark gains. A whole frame caption can be correct and still miss the object being asked about. The student therefore learns region tracking, depth perception, and temporal perception from a frozen teacher. At inference, those distilled signals let the model answer with grounded, dynamic understanding, rather than a loose video summary. Asymlock starts with the figure's asymmetry. Database images can use a large offline teacher, while the query image must run through a much smaller online student. The route follows detector descriptor distillation and geometry loss into the match visualizations, ending on the accuracy and FPS tables that show why moving compute offline matters. The practical lesson is that localization does not need the same model on both sides. The mapped world is stable enough to pre-compute strong teacher descriptors. The live device only needs compatible student descriptors, so matching stays lightweight while the final output is still a full 6 degrees of freedom camera pose. TTT-LRM starts at the Longview Streams and Motivation panel, then tracks how images are patchified into tokens that write compact information into fast weights. The callouts show distributed training as the signal that makes this state useful, then follow virtual views reading the adaptive state into 3D outputs, and finish on reconstruction results plus the attention cost comparison. The Intuition is an adaptive notebook. Incoming views update fast weights instead of making the attention window grow forever. Virtual view tokens then query that notebook and pass through a 3D decoder. The fast weights are test time memory, not ordinary retraining, which is why long context becomes manageable. Nitrogen's poster starts with public gameplay clips. Then the visible controller overlay turns those pixels into recovered actions. Those pairs scale into 40,000 hours of behavior cloning data, feed one vision action policy, and the result panels show that pre-training transfers better than starting from scratch. The paper's clever step is not just training an agent, it is converting internet video into supervision. A controller overlay is a label source hiding in plain sight. Once joystick and button states are recovered, many games become frame action demonstrations. The trained policy can then be evaluated as a general vision action model rather than a game-specific script. MacTalk starts by showing why a compressed continuous tokenizer collapses. If the decoder can ignore the latents, the latent space loses image structure. The figure then masks image patches with random and Dino-guided pressure, aligns compact continuous tokens to global and local features, and shows 64 and 128 token generation quality. The intuition is that compression needs a reason to remember. Random masks force reconstruction. Semantic masks force the tokens to carry object-level information. Global and local alignment keep those continuous tokens tied to the image. The goal is not an empty code with fewer numbers, but a compact code that still supports high-quality generation. Delta Talk begins with the old cost. Every future frame becomes a large spatial token grid and many forward passes. Delta Talk instead subtracts frozen Vision Foundation model features into one continuous change token. Delta World rolls those tokens into multiple futures with best of many training, and the right panel shows the efficiency gain. The paper's intuition is to predict edits, not pixels from scratch. Consecutive frames already share most content. A delta token stores what changed, and a world model can roll forward as a sequence of small changes. Best of many training matters because several futures may be plausible, so the model is not punished for not choosing one fixed path. V2 SAM first shows the ego to exo failure. A source mask cannot simply be pasted into a target view. The figure creates an anchor prompt from Dynov 3 matches and a visual prompt from mask pooled appearance. Lets anchor, visual, and fusion experts compete under P, C, C, S, and shows selected masks generalizing across benchmarks. The intuitive split is geometry plus appearance. Feature matches recover where the object might be, while pooled appearance says what the object should look like. Cyclic consistency then asks whether a mask survives the trip across views and back. The selected mask is trusted because it is self-consistent, not merely confident. Track on R opens on the real-world tracking gap, where teacher trajectories disagree across frames and no single tracker stays reliable. A verifier transformer scores candidates per frame. Synthetic perturbations teach it what drift looks like, and selected pseudo-labels fine-tune a student on unlabeled real video before the result panels quantify the gain. The intuition is selective trust. A whole pseudo-trajectory may be bad even when some frames are useful. The verifier turns reliability into a per-frame signal, so training can keep the trustworthy pieces and discard the rest. That makes unlabeled real video useful without pretending the teacher labels are clean. MSPT begins with the scaling conflict in neural PDE solvers. Local stress details and global pressure dependencies must both be captured. PMS, a partitions points into ball tree patches, adds pooled supernodes for global messages, and the error maps plus Pareto chart show that this keeps physics accurate while reducing memory and runtime. The visual distinction is important. Local points stay alive because they carry fine physical detail. Supernodes do not replace them. They carry long-range context between patches. The result is not just fewer tokens, but a structured compromise between local precision and global communication. SAM 3D body starts with in-the-wild body images and promptable inputs, then shows the data engine that mines hard images and fits high-quality human meshes. The model panel routes image, mask, key point, camera, and hand crop signals through shared features, body and hand decoders, and momentum human rig, while comparisons show why prompting and data scale matter. The paper's intuition is that full-body mesh recovery should not be a blind, single-image guess. Visible prompts disambiguate occlusion, rare poses, and hands. A rigged representation separates skeleton structure from surface shape, so the output remains editable and physically coherent. MAMA starts on the markerless close interaction goal, then treats dense surface landmarks as virtual anchors that replace physical mocap dots, while MAMANet predicts visibility and contact for each anchor. The MAMASyn panel explains where supervision comes from, and the Vicon results show why the same anchor route can be accurate, markerless, and usable outside a lab. The intuition is to preserve what markers gave us without wearing markers. Multi-view cameras see people through contact and occlusion. Dense landmarks, uncertainty, visibility, and contact cues keep the body rig constrained, so the red dots disappear, but structured correspondences still carry the motion. MatAnyone2 begins at the input video rows, compares older outputs that either harden boundaries or blur fine hair, then lands on MatAnyone2, preserving soft alpha detail. The abstract beneath the figure supplies the missing mechanism. The matting quality evaluator estimates which alpha pixels are reliable, scaling supervision into VM Real, so boundary fidelity improves across real video. The intuition is quality control at the pixel level. The model does not only ask for an alpha matte, it asks which alpha values can be trusted. That reliability map guides training and data selection, especially for hard boundaries like hair and backlit motion. Safari starts from the camera trap scale problem. Many wild clips across continents and species need more than isolated boxes. The figure attaches expert species tags and identity-preserving masklets to the same animals through time, turning messy conservation footage into a benchmark for full multi-animal tracking. The important point is persistence. A detection says an animal appears in one frame. A masklet says this individual animal remains the same object as it moves, overlaps, and disappears. Species labels, identities, temporal masks, and dataset statistics are attached to the same footage, making the benchmark closer to real conservation analysis. VGGT segmentor opens with projection drift. VGGT attention finds the object, but raw points land off target when ego and exo views change. The method panels fuse the source mask, guide representative points, refine the boundary, and the result panels show those corrections becoming IOU gains and cleaner masks under similar objects or occlusion. The intuition is that geometry gives a rough promise, not a final mask. Cross-view projection can say where to look, but scale change and occlusion break exact transfer. The union segmentation head turns that rough signal into a mask by combining fusion, point guidance, and boundary refinement. Retrieve and segment starts with a few pixel-labeled support masks, then follows selected visual prototypes as they are retrieved and fused with text for the test image. A small test time adapter turns that support into a per-image classifier, and the result panels show the supervision gap shrinking, including personalized object masks, without changing the whole backbone. The intuition is that examples make language specific. Text may say cup, but a support mask can say this cup style, this boundary, and this visual context. Retrieved prototypes and textual support reshape the classifier for the current image, while the backbone stays fixed. Malmo 2 begins at the architecture, where video frames and a text request become shared vision language tokens controlled by the attention mask. The data panels add captioning, QA, pointing, and tracking supervision, and the comparison panels show why open weights and data matter for video answers that can point through time. The intuition is that video language understanding should not stop at a sentence. A useful answer may need to point to pixels or track an object over frames. Malmo 2 makes weights, data, code, video understanding, and pixel grounding part of one open recipe. The richer figure pass changes the shape of the comparison. Each poster is a compact map of the paper: problem, mechanism, supervision, evidence, and usable takeaway. Across 3D assets, tracking, matting, wildlife data, physics, agents, and open vision language models, the shared direction is controllable perception. Recover structure from pixels, verify the supervision, compress the state, and ground the result so another system can act on it.
本演讲实录已收录至雷锋网 CVPR 2026深度专区，现已全面上线。专区不仅全面收录了重磅论文的工程化解读、专家前沿演讲，更将持续更新前方记者的第一手会议动态。扫描下方二维码或进入雷锋网 CVPR 专区即可查看。